Okay, in this problem, this is a little tricky, but once you see it, I think it's pretty straightforward. So we have two wires, and we have this thicker rail that's touching both of these wires. And the whole thing is in a magnetic field, and the magnetic field is into the page. And so what happens is this conducting bar, or rod, starts here at the vertex of these two wires and then moves up. So you can see its velocity is moving up. And so what you notice though, since it's moving, then my y is changing. But the nice thing about this problem is that this y and this y are the same. So our triangle is changing equally in the x and the y direction. And so it's saying, the first thing it's saying is find the direction of the induced current in the sliding rail. Okay, so how do you think about this? Well, my sliding rail, it's a conducting, the conducting bar. So this is conducting, which means all of the electrons, and I like to think about, whenever I'm thinking about current, positive charges and negative charges are free to move around. So if they're free to move around, what I have is I have a positive charge, say here, and it's moving up, and it's moving in a magnetic field into the page. So if I point my pointer finger up, and my middle finger goes into the page, then the force on this moving charge that's in the rod is to the left. So my force is going to be that way. So what that means is all the positive charges are going to want to move to this side. So all the positive charges in here are going to move to this side of the rod, and they're going to be stuck here. So there's going to be a whole buildup of positive charges here and a buildup of negative charges here. And so that creates a current. If I have a voltage, a separation of charge, I have a voltage difference. And so what's going to happen is my electrons or my positive charges are going to move to the left and then move around like this in this now loop that's created between these parts of the wire and this bar. So I can say here, find the direction of the induced current. It's going to be left in the bar or counterclockwise. And then this says, find an expression for the area of the triangle enclosed by the rails in the sliding bar. So I'm looking for the area here. And the thing to remember is that the area is going to be changing because my bar is moving up. So that's going to be, my area is going to be getting bigger. But if I think about area, my area for a triangle is going to be 1/2 base times height. And if I think about my base, say this is going to be my base, the y, and my height is going to be y. So that's going to be equal to 1/2 y times y, or y squared. Well, what is y? Well, we have an expression up here in the problem that says y is equal to velocity times time. So if y is equal to velocity times time, then my area is going to equal 1/2 v squared times t squared. And so that's part B. So A is equal to 1/2 v squared times t squared. So next, in number C, calculate the magnetic flux through the triangle. So the magnetic flux, so this is B, and this is C. So magnetic flux is given by phi sub B, and that's equal to the magnetic field B times the area. And so we can write that as the magnetic field is given by 1/2 Tesla. And then the v squared is going to be equal to 5 meters per second. Squaring that. And then t is in 3 seconds, so 3 seconds squared. And when we work that out, we get the flux is equal to 56.25 Tesla meter squared. So this is, magnetic flux is 56.25 Tesla meter squared. Next, it says calculate the induced EMF around the triangle. So this is part D. We're talking about induced EMF. And remember, induced EMF is equal to negative d phi dt, where phi is my flux, which we just calculated. So what we're going to do is we're just going to take the derivative of B times A, and that means the derivative of my B is a constant, so I can pull that out. And then my V is a constant, so I can pull that out too. So let's fix this. We'll say a negative B and negative or times V squared, and then I'm just doing d dt of t squared. And so that's the flux is gonna equal to a negative B V squared times 2t. And I'll go over here. So E is going to equal 0.5 Tesla. V squared is 5 meters per second squared times 2 times 3 seconds. And then when we work that out, we get EMF is equal to, and this is a negative, 37.5 volts. And our next one is E. What's the total resistance? So this we're working on E is equal to, E. I is equal to the EMF over the resistance, and that's going to equal 37.5 over 5, and so we get the current is equal to 7.5 amps. And then our bonus asks us to write the EMF as a function of t, and we write that as a t to the n. And if we let that equal to what we solved earlier, we get E is equal to, let's see where I put that. So the EMF is equal to, wrong one. So I can look back. Oh, right, here it is. B times V squared times T. And if we look at our formula, then we know that this is going to be A, and N, so T to the N is equal to 1. So A is going to equal B times V squared, and that's equal to 0.5 Tesla times 5 meters per second squared, and N is equal to 1. And so my A is going to equal 12.5 Tesla meter squared per second squared.